Hi class, so before we get going in with our GPS data collection and learning more about GPS, we need to review some basics from your cartography course. And what we're going to talk about today are the shape of the Earth. We'll go through review of geographic coordinates, geodetic datums, projections, projected coordinate systems, and then a little bit about map scales. And if you want to follow in your textbook, there's a little bit of reading, chapter 1, pages 10 through 13. So before we get started, I want to emphasize how important understanding your datum, your projection, your coordinate system, how important that is, especially when using GPS data. So you're going to go out and collect GPS data, and I think some of you might have already seen this a little bit in the lab on Thursday, that your points in your aerial photos weren't showing up in the same place. So you need to make sure that when you're merging GIS data from different sources, most importantly, you need to know what the coordinate system and the datum are of the data that you're merging. If you know what it is, and if that information is designated in your GIS data, your shapefile or your raster, then when you add it to the map will adjust or transform that data to make sure it matches the map. So a couple of things: you need to make sure your georeferencing is set in all of your GIS data when it comes from GPS, and then you need to know what the georeferencing is in your map and understand how that gets set. So I'm going to do a little screencast separately. So when you're using GPS data and you're combining it with existing GIS data or map information, you need to make sure your datum designation and your coordinate system, especially the projection, sort of goes along with the coordinate system in some cases. And then your units too, you got to pay attention to those. Must be known, and then eventually they need to be identical. Sometimes the transformation happens via ArcGIS without you actually having to do anything. So you at least need to know them so that the GIS can make them identical, so that your points plot in the correct place. So our output of GPS are coordinates. If you don't know what system those coordinates are in, your data are useless. If you don't know what data those coordinates are referenced to, what geodetic datum those coordinates are referenced to, your data are useless. So you could go out in the field, collect some data with your Garmin, write the coordinates down, come in and give them to me, and if you don't tell me these are UTM Zone 12, WGS 84 coordinates, I won't know how to plot them. So we need to make sure we know the datum and the coordinate system of any coordinates that you collect. Okay, so to get started with reviewing cartography, we have to think about the size and shape of the Earth, which is the branch of, interestingly, applied mathematics that deals with measuring the shape and the area of large tracts of country and helps us identify exact position of geographic points, curvature, shape, dimensions of the Earth. So Geodesy is the field that's looking at the size and shape of the Earth. And so why do we need to know? Well, if we're going to describe our position on the Earth, we need to know what the shape of the Earth is, so that we can represent that position on the surface of the Earth. So we need some sort of model that represents the surface of the Earth. And once we have that, we can apply a coordinate system to it. Once we have a coordinate system applied, then we can start identifying positions and finding coordinates in that system. So the first thing we have to do is say, what does the Earth look like? And very simplistically, we could say the Earth is a spheroid, just like this globe here, right? So we're saying that the Earth is a perfect sphere. We know that's not true. The Earth rotates about its axis, and it flattens at the poles, and it bulges at the equator and becomes what's known as an ellipsoid. So we could use an ellipsoid model for the Earth, but that's not perfect either. The polar flattening is about 20 kilometers difference in radius between the radius to the poles and the radius at the equator. Okay, so we could describe it as an ellipsoid, but more precisely, the Earth is actually what we call a geoid, which is kind of lumpy. It has some irregularities, and what happens is that the crust has different densities. So the oceanic crust is denser than the continental crust, and so gravity acts differently on these materials of different densities, creates some irregularities, in shape, it creates like sort of a lumpy surface, which we have to account for that if we want to make accurate maps. And so over here we could look at, okay, here's this dashed red line, that's the ellipsoid, and then the blue line is the geoid. And one way to think of it is if the surface of the oceans could conform over the entire Earth, if it were free to adjust to the effect of the Earth's mass attraction and the centrifugal force of the Earth's rotation. The topographic surface does not necessarily correspond to the geoid surface. So when we give the elevation, so let's say we measure the elevation on this peak, we're giving the elevation of that peak above some model of the Earth, and that model may be a reference ellipsoid, or it may be above a geoid. And you do have to be careful about your vertical datum, because your elevation will vary depending on what your reference surface is. And depending on where you are in the world, you can come up with those adjustment factors to see, okay, I got a height above the reference ellipsoid. How do I need to adjust my elevation to give the height above the geoid? So we need to know that the shape of the Earth, both for horizontal positioning and for our vertical positioning. Okay, so our coordinate system is the way that we're going to define our position. And a pair of coordinates are going to identify an exact point. So we stick a stake in the ground and we measure the coordinates for that position. And there are two main categories of coordinates that we'll talk about. One are geographic coordinates, which all of you probably are familiar with, latitude and longitude. And then we also have projected or grid coordinates. And what we've done there is we take our round Earth, we flatten it flat, and then put an XY grid on top of that. So that now we have northings and eastings, which are in linear units like meters or feet, which is a lot easier to work with than latitude and longitude, which are in angular coordinates or spherical coordinates.